All right, last time we started section 9.3, and 9.3 is applications and probability, and there's two different applications we're looking at. What was the application we looked at last time? It was odds, that's right. The other application that we're looking at this time is called expected value. Oops, there it was. So here's the definition for what expected value is. If we have the possible outcomes of an experiment, and we're talking about something that has numerical outcomes, so A1 through AN, and then they have corresponding probabilities of happening P1 through Pn. So they may be the same values, they may be different values for those probabilities. Then the overall expected value is A1 times P1 plus A2 times P2 all the way out to A sub n times P sub n. And we have a corresponding, going along with it, kind of definition of a fair game. In a fair game, we have an expected value of 0. Okay, so when we create that expected value statement, we compute it, it ends up being 0. So we're going to do an example of this, and I'm going to show you a couple different examples. The first one's actually going to be based on a roulette wheel, and we're going to go through a little bit about what a roulette wheel looks like so that you can think about the details of the A's and the P's that are happening in our description. So in a roulette wheel, there's actually 38 different slots, like pie shapes that they can land in, that the ball can land in. It's like a spinner. A roulette wheel is like a spinner, okay? The numbers go from 00 all the way up to 36. So you have 00 and 0, and then you have 1 through 36. One way, it's not the only way, but one way to bet on the roulette wheel is to bet on a single number. So you're going to say, I'm going to put $5 and I think it's going to hit the number 5 or whatever. $5 and I think it's going to hit the number 32. If the ball lands on your number, you receive your original chip back that you played, the original $5 in my description. And then you also get 35 more chips back from what you played. So the first question that it wants to know is, what's the probability that you land on 0, 0? So it's one of the equal-sized slots, and there's how many? 38. So there is a 1 out of 38 chance that you hit 0. 0, 0. And there's also a 1 out of 38 chance that you land on 0, right? Each slot has a 1 out of 38 probability. So when we're looking at this definition, which we're about to apply in a moment, all of our P sub n's, if I looked at individual numbers, are going to be 1 out of 38. Now, if I looked at evens, or if I looked at odds, or they have actually colors on this wheel as well, if you looked at color slots, it would be different probabilities. But an individual slot is only a 1 out of 38. So our question that we're going to think about, and this is actually, I wrote this a really long time ago, and it's something that he used to do. I don't know if he still does it or not. My father-in-law, my in-laws will occasionally go to locations where they will gamble. They always have a specific amount of money. They're not gambling addicts or anything like that, so I should have a bad impression of my in-laws. They kind of treat it almost like some of our children, and maybe you would treat an arcade. They go in, they've got an X amount of coins to spend, that's what they're going to spend, they're going to leave. So my father-in-law, though, would pass by a roulette wheel. He'll do it on cruise ships as well. I remember him doing it on a cruise ship when we went about 4.5 years ago. And they actually have a board next to it, sort of imagine like a monitor screen showing the last certain number of rolls or spins of the wheel. And he looks on the monitor, and if he does not see that the monitor has landed on 0 or 0, 0 in the screen, it's not on the screen, then he believes that that means that it's going to happen next. Okay, we know that doesn't make any sense, right? I mean, these are independent spins, but this is his mindset when he looks at this roulette wheel's history. So the question wants to know if he bets one chip on each of the numbers, so one chip that it's going to land on 0, one chip that it's going to land on the number 00, and each chip is worth $10. What is the expected value when he plays the roulette wheel? So there's actually a couple different options. One option is that he can win, and one option is that he can lose, right? He either wins some money because it lands on the 0 or the 00, or he loses all the money he bet, which is this 2 chips, because it lands on any of the other numbers. So not all the time, but oftentimes when we're looking at expected values, we're looking at things where we're actually winning or we're losing. So he has 2 different possibilities. One is the probability, or not the probability, but the option of him winning. and the other option is the option of him losing. So we're going to look at those two different categories, and we're going to consider what is the probability that he wins, and if he wins, how much does he win? And then what is the probability that he loses, and if he loses, how much does he lose? Okay, does that make sense? So those are our kind of broad categories. If you write down every single number, I don't really think that's a very time-effective thing to do. You're going to write down a whole bunch of stuff, right? This allows us to make categories that make it a little bit simpler, kind of like when we were doing our tree diagrams and we were saying, is it D or is it not D? Is it black or is it white? Instead of using all the balls, stuff like that. Okay, so if he wins, that means it landed on the 0 or the double 0, right? Okay, so what is the probability that it lands on the 0 or the double 0? 2/38, right? We had 138 and 138, so it's a 2 out of 38 chance that he wins. Okay, if he wins, how much did he pay to play? $20. You're right, okay? But how much does he receive back if he wins?
The 10 plus the 35 chips.
Close, yeah, you're close. So it's here and the original one chip. Yeah, so the one chip, the chip you played, there it was. So he gets 35 chips, plus he gets the chip that he played on that particular thing. Okay, so he paid two chips to play, and he receives back how many chips? 36, right? So the net amount that he actually receives back is 34 chips. Does that make sense? Right, he pulled out 2 chips, he gave it to him, they give him back 36 chips, but that's a 34 change in his pocket or whatever. So he's got 34 chips, and the 34 chips are worth $10 each, so how much money is that? $340. Okay, so let me actually write this out a little bit clearer, like with more of this. So we have our 35 that we win. I just want you to see where these, actually, you know what, let's do it this way. Let's write our 340 here, and then we'll put it over to the side how we did it. So our 340 comes from the fact that this is 34 chips. Our 34 chips come from the fact that we got 35 plus the one that we played back, and we played 2. When you're looking back at this later, I want you to remember where 340 came from. And then, of course, one chip equals $10, it said. Okay, so $340 is what he wins. So what's the probability that he loses then? 36 out of 38. It can land on any of the numbers 1 through 36. That's 36 different numbers out of the 38 numbers total. And if he loses, right, it lands on one of those numbers, how much does he lose? $20. So it's actually a negative $20, like in his pocketbook, right? It cost him $20. He didn't receive anything back. It's a negative 20. Does that make sense? Okay, you're going to need your calculator because you're not going to do any of this in fractions. You don't want to do that. So we're going to actually find each of these values. So we have 2 out of 38 times our 340. And we'll write it out with several decimals. This is money, so at least 2 decimals for now. You might want to write it with 3 decimals just because we're going to combine them here in a minute to make sure that we don't lose any accuracy. So I'll do 17.895. And then on the other one, I have 36 times, or divided by 38 times negative 20. So this is actually a negative 18.947. And then I'm going to add those two values together. And I am talking money here, right? I am. So I need to make sure that I record it with the accuracy of money, which would be 2 decimal places. So this is actually negative $1.05. So what does expected value actually find? Well, it finds what happens over the lifespan of doing this a whole bunch of times. Right? It's like with any other probability. You're multiplying by probabilities. So if my father-in-law does this a lot of times, on average, he loses about $1 every time he plays. Now, that's not really what happens, right? He either loses his $10 or $20, depending on how he does it, or he gains a whole bunch of money, right? One of those two things happens. But if you do this situation enough, it averages out, and this is the average loss per game, that make sense? So on average, he's going to lose, if you want to make yourself aware of the fact that that's what this negative is telling you, he's going to lose $1.05 every time he plays.
So did he do this once and it worked? And then
I think that's probably the general idea, is that the other thing, too, about my father-in-law is that he's a very lucky man. And I know that just sounds sort of like arbitrary, but I have a nephew who's like that, too. I mean, he got to go up on the stage with David Crowder one time. Like, what are the odds? They're not good, right? But, I mean, these are the things that happens, you know. I mean, it just seems like there's probably people in your lives, you probably have some, too, where you're like, things just tend to work out really nicely, and things don't work out with the probabilities the way they should. That's my father-in-law. He is a very lucky man. He's a hard worker, but he's also a very lucky man.
have you seen him win this?
I've seen him win other skills-based games. I haven't been around too much with the roulette wheel situation, but I know that he does this because my husband's told me he's seen it happen before. So, all right, we're going to do another one that's a game show. Are you familiar with the game Deal or No Deal? Okay, so if you're not, I start out with a whole bunch of cases, and if you go to like Chuck E. Cheese and Dave and Buster's, they have their versions of the same game, and they can play it. So my kids have played it before at these amusement places. So in our scenario, we're down to 2 cases, okay? So our 2 cases are being chosen. One case has $250,000 in it. That's nice. The other case has $10. If you're the banker and you want to give a reasonable offer to the contestant but not too lucrative, what deal would you offer and why? So we're going to figure out what the expected value is, right? On average, if we had 100, 200, 3,000, I don't know how many people doing this, what is on average that's going to happen, right? Obviously, the 2 different outcomes are actually $10 and $250,000 if the person plays out to the end of the game. Those are the real options. We want to see on average what happens. So we have our expected value. And while it isn't a probability of winning or losing, so I'm not going to write win and lose like I did on the last one, we do still have 2 options of things that can happen, right? So what is the value of one of the cases? $10. And what's the probability that that case that we have actually has $10 in it? At this point, it's 1/2, right? Because we're down, we've eliminated all the other cases. There is a 1/2 probability that our case, or the case we end up choosing, whichever one it is really going to have the $10 in it. The other option is that the case that we end up choosing at the end has a lot. $250,000, right? $250,000 in it. And what's the probability that that's going to happen? It's 1/2. Okay? So we're going to calculate this. So the first one would be 5. 10 divided by 2 is 5. And the second one would be 125,000, right? So what's my expected value? Yes, $125,005. Don't be tempted to sort of like add the 5 to the other 5. Different place values, right? Yeah, $125,005. So as the banker, we would know this, right? The computer would calculate it. The banker's not doing any math up there. Don't be thinking that. Computer's calculating it with however many cases are left, right? There's nothing special about this doing 2-case business, right? When there's 7 cases left, they can do the same algorithm. All the probabilities are 1/7. All the case values are in there, and it spits out a value that says this is an average at this point what we would expect this contestant to earn, or maybe earn's not a good word, win. All right, so as we are the banker, we want to offer around $125,000, right? There's not a specific answer to this in terms of this is my concrete number. But we want to offer something around $125,000. And if you're familiar with the way that the game show works, what they usually do is offer something slightly less, right? So that you feel like you're defeated if you take it. And so then you're going to go for it, and you're probably going to end up with that 10. I mean, maybe not, right? It's 50-50, but now you've put yourself in a position where you might. So we're going to be offering somewhere around $125,000 as we make this decision. If we'd had 7 cases left, the expected value that we would have got would have been the same sort of thing. We'd be offering around that $50,000 mark, or $22,000 mark, or something like that. Does that make sense? Okay. So it's not necessarily on this one where we're trying to make it fair. Notice the description doesn't say a fair game, right? We aren't trying to have an expected value of 0 in this case. We just want the to be a hard decision for the contestant to make, so we're using expected value for that. All right, their last example of this is going to use the lottery. I think the lottery is a really funny example. And the reason I think it's a funny example is because of the way it works. So oftentimes places want to, allow the lottery to happen, and they like to talk about, especially in Oklahoma, that the money goes to education. Y'all have heard this before, right? So I think it's very interesting because either the money goes to education, which means you want everybody to lose the lottery. And that somehow doesn't feel very nice, right? This doesn't feel very nice. We're rooting for you to lose. Or it means somebody wins the lottery and then there's no money to go to the education. So it seems like a lose-lose situation, to be honest, right? This does not seem like a very good idea, and yet we promote it that way. So I think the lottery is a very interesting one. So we're going to look at the way that they describe lottery as well, because this is another place where you hear people talk about odds. So in a given lottery, we know that the odds of winning the lottery are 55 million to 1. Also, the lottery is not a raffle. I think that's also a misnomer sometimes people have. Somebody has to win. No, nobody has to win the lottery. The lottery is choosing a bunch of numbers, and nobody has to choose the right numbers. And not only that, but multiple people could choose the right numbers at the same time, so why you also hear sometimes of people having multiple people winning. So nobody has to win the lottery. So the money really could go to education if that's how it really funnels down, I'll know, but nobody has to win. So the odds of winning this particular lottery are 55 million to 1. So if that's the case, what's the probability of winning the lottery? Remember how probability and odds are related? We talked about it last time, but we haven't probably done any work on it since then. Not exactly, but you combine some pieces. Do you have an idea, Kaylee?
Was it had to do with like parts one?
Yeah, so this is a part-to-part description, 55 million to 1. So these are the people that lose compared to the person that wins. For every 55 million losers, there's one winner. That's what odds would mean in this scenario. So what would the probability look like then? Part to whole. So we want the probability of winning, so that's our 1. How many people are losing? 55 million. But our denominator with probability is how many people played. Not 6. 55 million and 1. So it's not 56 million, by the way. That's 55 million 1. 0, 0, 0, 0, 0, 1, like that. Right? 55 million 1. Okay? I had a shirt upon a time. It was an adoption-related shirt for a family that we knew that was adopting 2 children. And it said 147 million minus 2. They were adopting 2 children. 147 million at that time was the number of orphans in the world. And I had one of the children in my house go, 147 million minus 2. That's 145 million. No, it's not. So careful on the place value. That's why I keep emphasizing it. It's just a really easy sort of like gut reaction thing to do. So just be careful. All right, so we have the 1 over the 55 million 1. All right, so in this scenario, the grand prize is 14 million, and a ticket costs $5. Okay? So this is often how these things work. If you see the Powerball going up high enough, it gets to values that are far beyond 14 million. But you've got some value of what you're going to win if you win, and then you've got the value that it costs you to play. So again, like our first scenario, there's just 2 options. You win or you lose. So as I'm finding my expected value here, you either win or you lose. Right? That's what expected value does, is it finds the expectation of those 2 quantities considered by their probability. So if we win, we just said we win 14 million. And I want to write that as 14 million. Okay? All out. 14 million. Now what's the probability that I win? Yeah. The 1 in the 55 million 1. Okay, so far so good. All right, cool. If I lose, what do I lose? $5. Now, I need to go back and I need to fix something. Any idea what I might need to fix? This isn't quite right. Yeah, 14 million is what I received back, but $5 I paid in. So this is like the chips problem that we did before, right? So right here, it's not really the 14 million at that point. It should be 14 million minus 5. So what should this number actually be? Yeah, lots of nines. 13,999,995. Good. All right, so now I've got my negative 5, and what's the probability that I lose? We didn't actually write that down anywhere yet. You got it. Good job, Caleb. It's 55 million over 55 million 1. These are really big numbers. If the number had even been larger, even the values we'd be working with could be even larger than this. But we're going to calculate this, and our calculator is going to be our friend for doing so. So I have my 13,999,995 divided by my 55 million and 1. And getting all those zeros and making sure I've got them right. Good news. 2, 3. And then I have, it's going to give me a value. Let me actually just write down the value that it gives me. The first value that it gives me is 0.25. I'll write a couple more just in case. 3 is probably enough, but I'll write 4. Did anybody else is given that? I just want to make sure I've got my zeros in there right. That look right? Lovely. And then on the other one, it's going to be negative because I've got a subtraction sign right here. So I've got 5 times 55 million divided by 55 million 1. And over here, this ends up being a bunch of 9s. I'll use 4 of them for now. Could just go ahead and round it off to negative 5. That would be okay. But what we want to do is we want to take that value and we want to add on. It's a negative value. And we want to add on the 2545. And we are looking at money, so we are going to round it at some point here to 2 decimal places. I have it being negative 4.75 if I round. The question actually asked, be careful you answer the question that's being asked. Is the game fair? What was our definition of fair game? So no. Yeah, the definition of a fair game is that the expected value is 0. Okay? Most carnival type games are not fair. That's the whole point. They're either being used as a money-making situation for the purpose of just making money, or maybe for the purposes of charity. But they're generally not actually being done in a way that's supposed to be a fair game. So this is definitely not a fair game. My expected value is negative. So this is not fair. And I don't mean it's not fair like I'm really sad. It's not fair. It's not fair mathematically. Okay, this is not a fair game by definition. Now, it's very interesting, though, because I mentioned earlier that many state lotteries proceeds are said to benefit education. So under these conditions, if all the proceeds benefit education and 1 million tickets are sold, what is the expected value from the lottery sale? So if the expected value of 1 ticket is negative 475 to the consumer, then that means that's the money going in the pocketbook of the person running the lottery, right? The state is the way that we've described it. 475 per ticket, but we have 1,000 or 1 million tickets, so what would we actually have to do to find out how much money is being made? Multiply them, right? I make 475 on a ticket on average, and there's 1 million tickets sold. So again, this is over the long haul. Over a large period of time, this is the expected situation. And so if I multiplied 4.75 times 1 million, this is money, what would I get? The decimal turns into a comma. It's 4,750,000. That's what I'd have, 4,750,000. But on an individual game of the lottery, that's really not a possibility, right? It's not. Either the possibility is that nobody wins, or the possibility is that there's a winner. And if there is a winner or more than one winner, they just split the pot. So it really doesn't matter to us whether there's multiple winners or not. So there's either no winner or there's a winner. Okay? So that's not really the outcomes that can happen. So it says, what are the actual possible outcomes? Well, the one possibility is that there's no winners. So if there's no winner, then I've sold 1 million tickets, and I sold them for how much? $5 a ticket. So it's really $5 that I'm having times my 1 million tickets. So I really end up making how much? $5 million. Okay, so one option is that the state makes $5 million. That's if nobody wins. The second option, of course, is that there is a winner, and they split, or one person gets the jackpot. The jackpot's $14 million. Well, I still collect $5 million from the sale of the tickets, right? So I have my $5 million that I originally collected, but now I have to pay out what? Somebody wins. How much do they win? Say it louder, Kaylee. They win $14 million. So I've collected $5 million, and I have to pay out $14 million. Do you see there's a problem with that, right? So now not only did we not actually end up making any money for education, we're actually now negative. I can tell you basically how they get around that in just a second. But this is a problem, right? This is not a good scenario if they're supposed to be benefiting education. So the second option is really that I'm down. This is $9 million. Okay, 3 more. So there's really just 2 options. Either we make $5 million or we lose $9 million when we run the lottery, if those are the conditions. And of course, those conditions are just arbitrary. So what really happens is that when you win the lottery is you generally have one of 2 options. You either have an option where you can take a full-time payout, and they don't give you the full amount. They give you like half of it or 40% of it, something like that. So you don't get the full amount at one time. Or they give you the full amount, but they make payments over the next 20 years. Okay? Because otherwise, what would they do to get the 14 million? Or at least the 9 million that they're short? They got a problem, right? So they have these different scenarios that are built up to help buffer that situation from actually happening. So interesting situation.